Hi friends, today we are going to learn about informed search in artificial intelligence. In informed search, the outlines are best first search, greedy first search, A** search and heuristics. We are going to the first method, the best first search. The best first search idea was use an evaluation function f of n for each node. F of n provides an estimated for the total cost that expands the node in to the smallest of f of n. The best first search implementation is ordered the nodes in increasing order of cost. The special cases are greedy best first search and AR searches. And the implementation of the best first search using the general search algorithm. The best first search algorithm is described as the picture. The algorithm is in the step 1, place the static node into the open list. If the open list is empty, stop and return failure. In step 3, remove the node n from the open list which has the lowest value of h of n and places it in the closed list. In step 4, expand the node n and generate the successor of nn. Step 5, check each successor of node n and find whether any node is goal node or not. If any successor node is goal node, then return successor and terminate the search, else proceed to step 6. In step 6, for each successor node, algorithm checks the evaluation function f of n and then they check if the node has been either open or closed list. If the node has not been in the both lists, then add it to the open list. Step 7, return to steps 2. For an example, this is the figure of the example. In this search example, we are using two lists which are open and closed lists. Following the iteration are traversing in the above example. This is the solution. In this, expand the node of S and put in the closed list. Initialization of open A, B and closed S. Iteration 1, open A, closed S and B. Iteration 2, open E, F, A and closed SB. Open EA, closed SBF. Iteration 3, open IGEA, closed SBF and open IEA, closed SBFG. Hence the final solution path will be the SBFG. In this kind of time complexity, the worst case time complexity of greedy best first search is obvious. We are going to next method, that is greedy search method. In greedy search method, the function greedy search problem is a solution of failure return best first search problem of h. H of n is equal to estimated cost of the cheapest path from the state at node n to goal state. F of n is equal to estimated cost of from n to goal. Example, f of n is equal to straight line distance from n to budget. Greedy best first search expands the node that appears the closest to goal. The properties of the greedy best first search: complete. No can get the stuck in loops OVM, but good heuristic can give dramatic improvement, and OVM keeps all the nodes in memory. Optimus now. We are going to the next method, that is A* search. The idea is about the A* search is to avoid expanding paths that are already expensive. Evaluation of function f of n is equal to g of n plus h of n. G of n is the cost so far that reach n. H of n is equal to estimate the cost from n to goal. F of n is equal to estimated total cost of path through the n to goal. Best first search has f of n is equal to h of n. Uniform cost search has f of n is equal to g of n. In A* search algorithm, we use search heuristic as well as the cost to reach the node. Hence, we can combine both the costs as following, and this is sum is called the fitness number. This is the estimated cost of the cheapest solution is f of n, and g of n is equal to the cost to reach node n from the start state h of n. That means that the cost to reach from n node to n goal node. A star search algorithm is the best algorithm that other search algorithm. A star search algorithm is optimal and complete. These algorithms can solve very complex problems. This is the algorithm of A star search. The step 1, place the static node in the open list. Step 2, check if the open list is empty or not. If the list is empty, then return the failure and stops. In step 3, select the node from the open list which has the smallest value of evaluation function g plus h. If node n is goal node, then return success and stop otherwise. Step 4, expand node n and generate all of its successes and put n into the closed list. For each successor n, check whether n is already in open or closed list. If not, then compute the evaluation function or n and place into open list. Step 5, else if node n is already in open and closed, then it should be the attached to the back pointer, which is the reflects the lowest g of n value. Step 6, return step 2. This is the example of a star algorithm. In this example, we will traverse the given graph using a star algorithm. The heuristic value of all the states is given in the below table. So we will calculate the f of n of each state using the formula f of n is equal to g of n plus h of n, where the g of n is the cost to reach any node from the start state. Here we'll use the open and closed list. The solution of the above problem is this. The initialization is s, 5, iteration 1 s a4 s g10, iteration 2 s a c4 s a b7 and s g10. The iteration 3 s a c g6 s a c d11 s a b7 s g10. Iteration 4 will be the final result as SACG. It provides the optimal path with the cost 6. Points to remember. A star algorithm returns the path which occurred first and it does not search all remaining paths. The efficiency of a star algorithm depends on the quality of the heuristics. A star algorithm depends on all nodes which satisfy the condition f of n greater than or equal to, less than or equal to, not equal to. Though complete, a star algorithm is complete as long as branching factor is finite, cost of every action is fixed, optimal. The search algorithm is optimal if falls below the two conditions, admissible and consistency. Admissible means that the first condition requires for optimality is that h of n should be the admissible heuristics for a star search tree. Admissible heuristics is optimistic in nature. Consistency. The second required condition is consistency for only A star graph search. If the heuristic function is admissible, then A star tree search will always find the least cost path. Time complexity. The time complexity of A star search algorithm depends on the heuristic function and the number of nodes expanded is exponential to the path of solution D. So the time complexity of B D, where the B is the branching factor. Space complexity. The space complexity of A star search algorithm is OFPD. We are moving to the next method, that is heuristics. A heuristics h of n is admissible if for every node n h of n is less than or equal to h star n, where the h star n is the true cost of reach the goal state from n. An admissible heuristic never overestimates the cost to reach the goal, that is, it is optimistic. For an example, HSLE n never overestimate the actual road distance theorem. If h of n is admissible, a star using the tree search optimal. This is the example for the heuristics. Therefore, the example of the 8 puzzle, h1 of n is equal to number of misplaced tiles, h2 of n is equal to number of Manhattan distance, that is the number of squares from the desired location of each tiles. H of 1 is equal to 8 and the h2 is equal to 3 plus 2 plus 1 plus 2 plus 2 plus 3 plus 3 plus 2 is equal to 18. This is the correct answer. And this is the end of our section. Thank you.